Alright, we have 15 seconds to wait for people who's not here yet. Any question? Anything you want to discuss? Otherwise, please sign your name. Anyone haven't signed your name yet? Okay, give him the sign-up sheet, please. Okay, let's start. I post the video on YouTube, and if you put my first name and last name in YouTube, you can find our video. Okay. This one is number 5. It's not that clear. Okay. It's not that clear. So when you use it, you can use your slide in the Blackboard, or you go to this website to download the PowerPoint file and follow it. It will be clearer if you use your PowerPoint file. Please give her the sign-up sheet. Last time we talked about the calculation of temperature profile. Okay. Any question on the homework? Yes. What's your name?
My name is Tope.
Tope.
Yeah.
Oh, okay, that's easy. Okay. Question, yes.
I had a problem with the pressure gradients plot. Yeah.
You did the pressure gradient plot?
I had a problem with it. I didn't get it.
You didn't get what? Temperature?
No. The pressure against depth. The plot of pressure against depth.
Depth or distance?
Sorry, distance.
Okay.
Distance of pipe. Yes.
Alright. Did you get temperature profile?
Yes, I got that.
Okay. Can you calculate temperature at every location?
Yes, I get that.
Okay. Without doing any integration, can you average them?
Yes.
Okay. For the average temperature, can you calculate viscosity at that temperature?
Yes.
Alright. After you have that temperature, viscosity at that temperature, can you calculate Reynolds number?
I did that.
Alright. What about friction factor?
Did that.
Okay. What about 2F rho V square over D?
I did that.
You did that. That's a pressure gradient minus dPdZ. In this case, gravitational term is 0. We neglect any accelerational term. So minus dPdZ equal to 2F rho V square over D. So you got it, right? You got the value.
I got the value, but to plot non-zero was a challenge.
Okay. How much do you get?
I mean, okay, I was expecting it was going to come like this, but I got something like this, so definitely something was different.
So minus dPdZ equal to what? How much? 10, 20, 30, 40? Some number, positive number. Positive number or negative number?
Just positive.
Positive number, real number. Minus dPdZ equal to some value, positive value. So this means we assume that in the whole pipe, it has only one pressure gradient. Pressure gradient is the same everywhere. Let's say we get that pressure gradient equal to 100. Okay.
I think I got something like 40.
40.
40 point something.
40. Okay. Let's say 40. So if you have minus dPdZ equal to 40, can you plot pressure profile? Do you have inlet pressure?
Yes.
Okay. Inlet pressure, can you convert that inlet pressure to the unit of Pascal?
Yes.
Okay. So if you have minus dPdZ equal to 40 Pascal per meter, so this means every meter pressure drop by 40 Pascal. Does it make sense?
Yes, it does.
So this means at the inlet, okay, at the inlet, 100,000. Next point from the inlet, which is 1 meter away, will be 100,000 minus 40. The point after that, 2 meters away, will be 100,000 minus 80. Keep doing this until at the end.
Good.
You have 15 minutes more after the class.
I've submitted actually.
Oh, you submitted already? You can resubmit it. The submission limitation is unlimited.
Okay.
Okay, download it and correct it and submit it before 10:50. Yes.
All right.
You said the DPDC will be constant. But
Doesn't need to be constant. That's the approximation. There are several ways of doing it, and most of the time, you can get best approximation, not the right answer. Okay. To do it very good, what you can do is discretize it into several sections. Okay. Discretize it into several sections. Then calculate viscosity of each section. Right? And calculate, oh, what time is it? 9:05 and about to be 9:06. Who is missing from the class? Where's Nguyen?
I don't think he knows that we're supposed to show this 9 today.
Oh, you don't really know. Well. Look at this. 9 to 9:50, pseudo single phase. Can you text him or call him? He still have time to come until 9:30. After that, he can still come.
We want to talk to him?
No, I don't want to. So, last time we have pressure along the pipe, right? Temperature along the pipe. What we can do is we discretize it into several sections. Calculate viscosity of each section. Then get friction factor of each section. Okay. Then calculate minus dPdZ of each section. Calculate pressure drop of each section. And then add them together. We get total pressure drop. Good? Seems to be good, right? It is good to a certain point. Whatever we do, without doing the full calculation, we get just best approximation. The reason I say that is, let's say we have, okay, right now is what? 9:07. It's 9:07. You can let up to 6 times, but you can still get A. Okay. If you let at the back of your signature, say late. Okay, for me, please. So I think that because if we have temperature change with distance, we will probably have a density change with distance, right? So when the temperature drop, density kind of what? Go up, right? It's condensed a little bit, it shrinks a little bit, right? So velocity will change a little bit. When there's a little bit of velocity change, you will have a little bit of acceleration or pressure loss. But that's very small, we can neglect it. A big thing here is the change of phase. If we have flow in the long pipeline and we have enough pressure drop, when we have pressure drop, gas can come out of solution. Okay, let's say initially we have 100% liquid. When there's a lot of pressure drop, depending on where we are at on the phase envelope, it is possible that gas come out of solution, right? So that's why in the homework we make several assumptions to make it easy. Okay. Why do we want to know how to do any of that easy calculation? What do you think? Maya, why do we want to do that kind of easy calculation with assumption? Why do we do that?
Because the hard one needs numerical method, I think.
Oh, correct. The hard one needs numerical method. Okay. What's your name? Chang? Chia. If you have, did you do homework?
Yes.
Okay, you did. So if you have software, do the calculation, do we still want to do it by hand?
Yeah.
Really? Okay. Next, Yahweh. If you have software do the calculation, do you still want to do it by hand with some approximation?
Yes.
Why is that?
I'll let you like check
Check what?
if that I mean to check the answer with the
You want to check the answer.
yeah.
Okay. Okay, Raymond, how do you check the answer?
Well, you solve by hand and get an approximation of the answer, plot it out, and compare with your computer-generated result.
It should be close, right?
It should be close.
So if we make several assumptions to make it easy to be able to do hand calculation, and then we do full calculation in commercial software, where is the sign-up sheet? Let me have it, please. So when we do full calculation, if you get 50 psi pressure drop when you calculate by hand, and you get 5,000 pressure drop when you do it by computer, what do you believe?
Someone's wrong.
One of them is wrong.
Well, one of them is wrong.
One of them is wrong, or both are wrong. Okay. So if you do it enough, you will see that just software is great, but there's several opportunities to make a mistake, right? Okay. So you want to check it by hand. Do simplified version of the calculation and check. Okay. Like if somebody else do the calculation for you and say, okay, I use $1 million software, get the result. Do you believe them? Yes, right? But you still want to do recheck. Okay, you still want to do recheck. Alright. That is George, right?
Yes.
Please come sign your name, okay? And write down the lead at the back.
Yeah.
Please. So last time we have temperature profile calculation. Okay, we skip this. Okay, for RK45. For explicit Euler, I think you can do it. Okay, for explicit Euler, and you actually have done it already when you do some kind of pressure calculation. Raymond, please help me. I need an annotator. How do I make it pop up, the annotator? Sorry. That should do it. It's all like that, but I want it on the computer screen. Please. Doesn't work, right? Okay, it's okay. You have minus dp by dc, right? So plus dp by dc will be something more than 0, positive value for pressure drop. So this is a slope, right? dpdc is a slope of pressure versus length graph. So what you do for explicit Euler, we use the slope at the current point to calculate the next point. The slope at the current point is something like this, right? So we extrapolate and then we stop at the next point. Once we are at the next point, we stop at this point and use the slope at this point, get the value at the next point. Okay. Okay. Mathematically, you will get P at next point equal to P at the current point plus slope multiplied by delta Z. That is how we plot pressure versus length, right? Okay. So it is easy. We use the slope at the current point. It is easy because the slope at the current point is defined based on the fluid property at the current point. We don't have the fluid property at the next point yet because we don't know what is the temperature and pressure at the next point, right? So first we start with fluid property, viscosity at the current point. We have viscosity at the current point, density at the current point. Then we can calculate Reynolds number at the current point. Then calculate friction factor. Then, okay, neglect the gravitational term, neglect accelerational term. Then we have 2F rho v squared over d equal to minus dp dz. And of course, we get dp dz, right? That is the slope based on the fluid property at the current point. Okay, that is the pressure drop per unit length based on the fluid property at the current point. And then we get pressure at the next point by current point plus slope multiplied by delta Z. Okay, so that is explicit Euler that you're doing. Okay, explicit Euler, it works for this homework. In some case, it doesn't work. Okay, the case that it doesn't work is when there's a big change of fluid composition or fluid property with temperature and pressure. So let's say we have fluid property at the current point and we want to calculate pressure at 10 miles away. And we set delta Z equal to 10 miles. We set delta Z equal to 10 miles. And we are on the phase envelope where it is possible to form gas when there's a pressure drop. So what happened is we use fluid property at the current point. Try to calculate pressure at the point 10 miles away. It doesn't work, right? Because fluid property change with distance. So in that case, if we jump too far, it doesn't work. Okay? It works, but the result is not right. We can easily solve it by jump smaller, jump shorter distance. Instead of jump 10 miles, okay, let's jump 0.01 miles. Then it may work. There's a better way of doing it, okay, and more stable way may be implicit Euler or RK4, RK45, RK4 and RK45 is an explicit scheme. We don't talk about that. We will talk about that later in numerical method class, okay. But just so you know that explicit Euler does not always work, but it's easy. We use the slope at the current point to get the value of the next point. Okay. George?
Yes.
If we have the way to use a better numerical method, like RK45, we have the result of that. Do we still want to do explicit Euler calculation?
Maybe to check.
Oh, correct. Yes. We always want to do easier numerical scheme to check if they are matched or not. Okay. A big reason is if we do the code by ourselves, we get the result. We will not know if that is correct or not. If you do it for the first time, cannot check the answer with your peer. No one know the answer before. How do we know that we did it right? We don't. Okay. The best we can do is we can check with the easiest scheme and try to see if the order or magnitude match or not, or the result makes sense or not. I think you have enough about this thing. Okay. And better numerical scheme will be taught in the numerical method class. Oil water flow pattern. We are in single phase flow topic for a while, right? Now let's move to two-phase flow with oil water. Oil water flow pattern can have stratified flow. Okay. Stratified flow. Stratified flow. So what's there on top? Maya, what's there on top?
Gas.
We have oil water flow. So what should stay on top?
Oil.
Oil, okay. Because it have lower density, right? It's kind of lighter. We can have stratified and mixing at the interface. Okay. Some oil stay in water, some water stay in oil. So top part is oil. Oil is white. Water is gray. Okay. So when we have DO/W is the disperse of oil, disperse of oil in water. So water is gray, right? So we have oil in water, which is white in gray on the top part. So this flow pattern is disperse of oil in water and water layer. We have water layer at the bottom. Okay. But on the top is oil and water, and we have water at the bottom. In some cases, we can have full dispersion of oil and water. Alright, so we have fully mixed oil in water. Water is the continuous phase. Oil is a discontinuous phase. We can also have dual dispersion. So we have water as a continuous phase on the bottom and oil as a continuous phase on the top. So we have disperse of water in oil and oil in water simultaneously. Right? We can also have disperse of water in oil. What time is it? Come here, please.
Naturally.
Oh, 9:22. Okay, sign your name and say at the back that you are late and return the sheet to me, please. Okay. Thank you. Alright. How do we know that we have which flow pattern? Yes.
Can we, dispersion phase, or what you call dispersion, can we call it emotion? Is this same as emotion? Or not the same?
Emulsion is kind of stable. Emulsion of oil in water means that if you wait 10 seconds, it stays like that. So it's kind of stable emulsion. If you wait 2 months, it's separate. So we may call it dispersion of oil in water instead. If you wait and then it's separate. So like on the bottom one, if we wait 5 minutes, maybe it's separate, or if we wait 10 seconds, it's separate. So we don't want to call it emulsion. Emulsion tends to not separate at all. Okay. The way to know which flow pattern we have, we can use flow pattern prediction program from Torello 1999. You don't have it, it's not commercially available. Okay. But I have used it before. Basically, we just click a button. Click the button and it shows flow pattern map. Nice, right? So we may actually have to reprogram it if we want to use it. Tulsa University have this. and we have to pay a membership fee to get this. Okay. Now we shall talk about how to read the flow pattern map. Okay. Look at this part. This axis is V subscript SW. VSW, we call it superficial water velocity. Okay, that is VSW. VSO is superficial oil velocity. Superficial means it's not real. Okay, it's not real. Superficial water velocity defined as water volumetric flow rate QW divided by AP. AP is the pipe cross-section area. Okay, AP is the pipe cross-section area. So, and VSO is QO divided by AP. To read the flow pattern map, we want to know superficial velocity of oil and water first. After that, we read the chart. For example, if my VSW equal to 0.5 and VSO equal to 1.5, so what I do is I put all the fluid property, pipe geometry into the software, click a button, it shows the flow pattern map. For this flow pattern map, it is for the case of inclination angle of 0. Inclination angle of 0 means horizontal flow. Okay. Density of 850, water density of 1000 kg per cubic meter, oil viscosity of 15 centipoise, diameter of 2 inch, and water viscosity of 1 centipoise. Interfacial tension of 30 Dan per centimeter. Okay. So if we run the flow pattern map for other inclination angle, the map doesn't need to be the same. Most of the time it changes. If we run for other viscosity, the map will change. If we run for other diameter, it will change. How much it changes, we have to run it to know it. Okay. For this case, if VSO is 1.5, so we go to VSO. Okay, that is VSO 1.5. Or this one is on the log scale. Okay, 1.5. I think. Let me do some calculation. Log base 10 of 5 equal to 0.698, about 0.7. Okay, log base 10 of 5 is about 0.7. So 1.5 is about over here, 0.7 of the scale. Okay. So VSO of 1.5 is over here. It's not at the half because it's on the log scale. It's at about 0.7. Okay. 0.7 of. Oh, sorry, over here, not over there. No, not this one, So the first one is 1, the next one is 2, and 1.5 is about here. 0.07 of the full scale from 1 to 2. This is from 1 to 2, approximately 0.3. So we start from here. 0.5 is 0.1, 0.2, 0.2, 0.3, 4, 5, maybe somewhere over there.
I think it's
They did it wrong again. Because that is 1. So
between the first and second one.
let me clean the screen. So how do I do it right?
The second one next to
Between,
one.
yeah, between first and second.
Between
It's just
VSW of 0.5, where is 0.5? Over here? 0.1,
0.2.
0.2 is over here. 0.3, 0.4, 0.5, 0.6, 7, 8, 9. So maybe over there is 0.5?
Yeah,
Did I do it right this time?
Look at the one on the right.
The first one.
Look at the one on the right.
Yeah, the one on
Good
the side.
idea. Point 1, point 2, point 3, point 4, point 5 is about that. That is point 5. And 1.5 is 1, 2. So 1.5 maybe about that, right? That's 1.5. 1.5 and 0.5. I get X. X symbol here is disperse of water in oil and oil in water because it's over here. If I do it over here, it's about green thing over here. Yeah, dual dispersion. Alright? That's how I read the graph.
Professor,
Yes.
to derive this map, did they use empirical equations and relations, or there's a science behind it?
It was done similar way for the case of gas liquid. I haven't talked anything about that yet.
So it's
For this one, they have some experimental data and some model to do that prediction. It's a mechanistic model, partially based on empirical data. Okay, most of the stuff based on the actual physics of the phenomena. So, does it make sense for this one? Let's take a look more closely. So, VSO means superficial oil velocity, right? When we add more oil, we change from dual dispersion to dispersion of water in oil over here. That is water in oil. That is when we have more oil. If we have less oil, it becomes dual dispersion and it may become stratified. So if we start at this point and we add more oil, so we are at stratified flow regime, add more oil, we get stratified with mixing at the interface, add more oil, we get dispersion of water in oil. Does it make sense to you? Alright, so what happens when we add more water? So when we add more water, so if we add more water, we start from stratified. When everything is slow, we have stratified flow. Make sense? If everything is slow, we have stratified flow. When we add more water, we change from stratified to stratified with mixing at the interface. This one. So when we flow water faster, has more water flow rate. When we flow water even faster, we get this yellow thing. Dispersion of oil in water and water layer. We start to have water layer at the bottom when we flow more and more and more water. If we flow just water, we have single phase flow of water with no oil, right? Correct? Or oil maybe just small part on the top. If we add more and more water, so we have dispersion of oil in water. So when I see this, first thing that I think is, okay, we flow water, we can change from certified flow to like fully mixed of oil in water. I guess that is because the turbulence from water mix or break oil into several small droplets and disperse throughout water phase and become like this, right? If we flow water very quick. Okay, so Triolo proved that this prediction, prediction match with their measurement. Okay, so we can trust it. If we flow slow, do we always have stratified like this? Oh, let me call it Tolani Afolabi. If I have oil and water, I flow it slowly. Is it for sure that I will have stratified flow like that?
It's possible.
Possible.
Can you show the other graph?
For that angle, okay, for that angle, that fluid property, it will be like that. Is this the prediction for the region close to the inlet or far away from the inlet? Or it doesn't matter?
Okay. Very good.
Okay. Tope, you already did it your way. Oh, Vega. Okay, see this flow pattern map. See this flow pattern map? Is that flow pattern map for the region that is close to the inlet or far away from the inlet?
Well, I think that you would probably have like a steady state flow, so maybe like far from the inlet.
Far from the inlet. I would think so. Because what? At the inlet, if I have, okay, cross-section view like this, on the top, I have water inlet. And on the bottom, I have oil inlet. So, right at the inlet, oil will be injected from the bottom and then go up, right? Water will be injecting from the top and then go down, like that, right? So, inlet condition may actually matter. Okay? But away from the inlet, yeah, I think this happened, the flow map that they have happened. Okay? So distance from the inlet can matter. Okay? Alright. What I want you to know from this graph is what happened when we flow everything slow. And what happened when I flow oil fast but a little bit of water. And what happened when I flow water very fast and a little bit of oil. You should be able to say, hey, this burst of water in oil is for the case of flow oil very quick, right? And a little bit of water. You should be able to say that. If you say otherwise, you say, okay, this burst of water in oil happened when we try to flow water very quick and slow oil flow rate. That is wrong. Okay? So you should know this. For example, in closed book exam or something. Alright, how do we do calculation? Oil water dispersed flow. For oil water dispersed flow, first thing that we want to know is, can we assume it as a single phase flow and do the calculation? Do you think can we assume that it is a single phase flow and do calculation?
No.
Yes, to some extent. Okay. Depending on what flow pattern. So if we have stratified flow, no, we cannot assume it as a single phase flow and do the calculation, right? Because there's a slip between the phase. Actual velocity of oil and actual velocity of water doesn't need to be the same. Okay. But if it is fully mixed like this, oil water or water in oil like this, it's kind of fully mixed. For a fair approximation, we may say there's no slip between the phase. Okay, and both of them has the same actual velocity inside. So for fully dispersed flow, we may assume that it is act as a single phase flow. Okay, so like we assume that it's from emulsion or something, and then it flow. For that case, that we can assume fully dispersed flow, we will say oil hold up equal to no slip hold up. No slip hold up means the actual velocity of liquid, of oil, and the actual velocity of water are the same. So if I have some particle in oil phase, it moves at one speed. Particle in water phase, it has to move at the same speed. Okay, so there's no slip. That's what it means. If we have highly turbulent flow, fully mixed, it is very likely that we have no slip, right? If we have kind of laminar flow, phase separation happen, like stratified flow, so it is likely that we have slip, right? So if we have stratified flow, and we have the same volumetric flow rate of water and oil, so we have same superficial velocity. Not here. Okay. I don't remember how to pronounce it, but June. Okay. So if we have VSW and VSO the same, so same pipe cross section area, same water volumetric flow rate to oil volumetric flow rate. Top part or bottom part, which phase should flow faster? Actual velocity. So when we have stratified flow, we drop some tracer, or we have some ink over here, ink over there. Which one should flow faster? Top or bottom? Given that we start at the same superficial velocity, or it should be the same?
It's the same.
Okay. So if we start at superficial velocity of water equal to 1, superficial oil velocity equal to 1, so superficial velocity is the same. We have stratified flow. So you think the actual velocity will be the same, right? We will show you in the next lecture, not in this lecture. Think about it for a while, okay? Think about it for a while. But when we look at this, I can tell, okay, this is oil velocity. We say this is V oil, actual oil velocity. Yuan Chan Li. Okay. Actual oil velocity, which is VO, and superficial oil velocity, which is VSO. Which one is higher? Guess one. It's one or another. You can say the same, but the same is wrong.
The VSO should be higher.
The VSO should be higher. Danny Perez. Okay, VO is the actual velocity of the top phase. VSO is the volumetric flow rate divided by pipe cross section area. Let me show you the equation. This is VSO. Between VO and VSO, which one is higher for stratified flow?
I think that VSO.
VSO is higher.
Superficial.
Superficial velocity is higher. So you agree with Nguyen?
Yes, because
okay,
superficial.
all right. Let me ask next. Sweta, which one is higher?
VSO should be higher.
VSO should be higher. Okay. Muhammad Ramadan, not here.
Somebody answer me.
Siri, which one is higher? VSO or VO?
I think VO, because you keep asking.
Okay, so if I calculate VO, what I would do is I use volumetric flow rate divided by that cross section area, right?
Which is smaller.
That is VO. When I calculate VSO, I use volumetric flow rate, same volumetric flow rate, but divided by larger cross section area. Okay. So Nguyen and Dennis, would you like to change your mind? A little bit? Probably, right? Okay. So for stratified flow, actual velocity is higher than superficial velocity. Superficial velocity is volumetric flow rate divided by the whole pipe cross-section area. But the actual velocity is volumetric flow rate divided by just the cross-section area that is occupied by that phase. Okay? So, yes?
So is this only true for stratified flow? If you have like the stratified meets the second one? Would you
the second one. Okay. So, we have oil in here, right? The real question is, okay, oil over there and oil which is that droplet, do they travel at the same speed? I doubt. I don't know, but I don't think so. They may not travel at the same speed because one of them move through oil medium, right? And there's no, it's like, it is the shear of the fluid particle against itself in medium of oil. Another one is the shear of oil droplet in water medium. Water and oil doesn't have the same viscosity. Most of the time, oil is more viscous. So I think it may not be the same. But if we are looking at the actual velocity of oil, this part of the continuous phase of the top one. So you may guess, and probably it's right, because VO should still be higher than VSO, because VSO is divided by the whole pipe cross-section area, but VO is just the top part, right? We may have some error because of this droplet, but it's a little bit, so it should not be much error. So in this case, stratified with mixing, actual velocity is still faster than the superficial velocity. Okay. So, okay, next. Arya, in which case do you think that superficial velocity will be equal to the actual velocity?
The dispersion of oil in water?
When there's no slip, right? So, no slip means it moves at the same speed. So, okay, next. V-ton. In which case that you think superficial velocity will be faster than actual velocity? Is it possible? Which case? Yes? So, if we ever have backward flow, but on average it's moving forward, this means the actual velocity at that particular moment when it flows backward, the velocity is negative, right? But on average it's positive. So in that case, superficial velocity can be higher than actual velocity. You haven't seen it yet. I'll show you in the next lecture. It's possible when you have backward flow. Okay. Okay, you are here. So, no slip liquid hold up. And do you see no slip liquid hold up?
You've seen it before.
Lambda. You see this one, right? This lambda. No slip liquid hold up.
Yep.
QO divided by total flow rate. Can we calculate it without doing the test?
Something like GOR or?
So if we know inlet oil flow rate, inlet water flow rate, can we calculate no slip liquid hold up?
Yeah.
Yes, right? Can we calculate actual liquid hold up without doing the experiment? Maybe not. Yeah, most of the time it's no. It is about 9:50. I should let you go and come back at what time? 11, right? 1:10. So we will come back at 11 in the room 110. We will talk more about this and then watch some video and have homework. Okay? See you soon. Bye bye.